Alright, I'm going to be showing you one example of graphing a piecewise function, and this function is going to have 4 different pieces to it, and then after that I'm going to show you all the different concepts related to that, whether it be the x and the y intercepts, the increasing, decreasing, domain and range. It is one lengthy example, but it includes every conceivable concept I can think of related to this topic. So if I talk too fast, you have the luxury of putting me on pause and stopping me, rewinding me, or turning me off altogether. Alright, this is our function f of x here, and notice it is defined in 3 different pieces. I'm going to call that the red piece, this the blue piece, this the green piece, and this the orange piece. Alright, now I'm going to do this graph 2 different ways. So after I finish this entire problem here, I'm going to graph it again. So when I'm done with this part F here, when I'm done with part F, you can just, if you feel like you understand the graphing, you don't have to watch the next portion. But I'm going to do it 2 different ways just to give you 2 different options on how to graph this. Okay, so first of all, it's important that you notice the first red piece is a quadratic, so because it's degree 2, and so it's a happy face or a sad face. Since the coefficient of the square term is negative, it's going to be a sad face. That plus 3 moves the graph down or up 3 units. So my vertex is at 3 here on the y-axis, and it's just a sad face. Alright, now I could plot a bunch of points to find out how wide this thing is and make it more accurate, but for this purpose I'm just trying to do a sketch here. Now the remaining pieces, the blue piece and the orange piece, those are linear functions in slope-intercept form, y equals mx plus b. So the y-intercept of the first one is a -3, so I'm going to put a -3 there. And the slope is a 2. The coefficient of x is a 2. So from that y-intercept, I'm going to go up 2 steps and over 1. And between any 2 points is a straight line. Okay. Now I'm going to skip the green piece because notice the domain here. It says x is equal to 2, and that's kind of weird. So I'm going to skip that. I'm going to go down to the orange piece. In this case, the y-intercept is a 2. Okay, and oops, I have to shift this around a little bit. Alright, the y-intercept is a 2 and the slope is a -2. So I'm going to go down 2 steps and over 1. Remember, the slope is rise over run, and that's -2 over 1 if we make that a fraction. So from the y-intercept of 2, I go down 2 over 1, and between any 2 points is a straight line. Now back to the green piece. Notice it's equal to 4, and there's no variable there, so there's no slope. It's really just a horizontal line at 4. Well, here's 4 on the y-axis, and it's really just a horizontal line. Okay? So that's how you would graph 4. It's not 4x, it doesn't have a slope or anything. Now, this is, you have 4 pieces, and as you can see on the graph, there are 4 different graphs. But all of these pieces have a restricted domain. And what I mean by that is, if you notice all these conditions here, it says if. And so I call this graphing that I'm going to do, I call it the erase method. So what I do is I graph all the pieces first on the same graph, and it looks like this huge mess. Now, this graph that you see here is not a function. It horribly fails the vertical line test. So what I'm going to do is I'm just going to take each piece. Notice that the red piece is only defined numbers that are less than 0. So what I'm going to do is, first of all, I'm going to erase all this here. Okay. This red piece is defined for numbers that are less than 0. So I'm going to go to 0 on the x-axis because this is the whole domain. This whole thing here, okay, is the domain. And the domain of the red piece is strictly less than 0. And so the red piece, I'm just going to go to 0 on the x-axis, and I am going to put a big fat hole there. The reason why it's a big fat hole is there's no less than or equal to bar. It's strictly less than, okay? It's strictly less than. So I'm going to put a hole there. And numbers that are less than 0 are to the left of that. So I'm going to erase everything to the right of that. Whoops. Let me put my little pieces back there. So the only thing that I'm considering for the red piece is that little cascade to the left. Those are numbers that are less than 0. Now let's go to the blue piece. The blue piece has a domain between 0 and 2. So I'm going to go to 0 on the x-axis, which is right here. And notice that it's less than or it's greater than or equal to 0. So I'm going to put a big fat dot there. Okay? And it ends at 2 on the x-axis. So I'm just going to go to 2 on the x-axis, hop up on the curve, and I'm going to put an open circle there, okay? Because once again, there is no less than or equal to bar. It's just strictly less than. So I'm going to put an open circle there. So the blue piece has a beginning and it has an end. So it's like a fragment, okay? So I'm going to erase everything to the left of 0 and everything to the right of 2. And I'm having a hard time erasing just that, so bear with me here. Okay, so the blue piece has a beginning and it has an end. Now let's look at the green piece, all right? Now this is kind of unique. Anytime you see this equal to thing here, what you're really going to have is you're just going to have a dot, a single dot. So the graph is only equal to 4 at 2. In other words, at 2, 4 is one fat dot. 2, I'll go to 2 on the x-axis, go up to the green dot, the green graph, and it's at 4. Everything else I erase. So that pretty green line that I drew horizontally is gone. All I have, and I'm going to put it back as a green dot to stick with my color scheme here. So this fat dot here is suspended. It's floating up at 2, 4. Now on to the orange piece here. Notice the orange piece also has a beginning. It begins at 2 and it ends at 4. Okay? So it starts at 2 and it ends at 4 for the orange piece. Okay? Now I'm going to be putting an open circle at that because, once again, at 2, it is open. So I'm going to put a big fat open circle here. But at 4 on the x-axis, this is 4 on the x-axis, it is solid because it's less than or equal to. So I'm going to put a big fat solid dot there. And I'm going to erase everything to the right of that 4 and everything to the left of 2. Okay, everything to the left of 2, and apparently I'll be erasing everything else that I drew. Let me put that back. Okay, so pretty messy, huh? We have this red cascading thing, we have this blue fragment, we have this suspended dot, and we have this orange piece between 2 and 4. Okay, these pieces are not to scale here. It's just a sketch, and using that sketch, I can answer all the little parts here. Okay, so one purpose for having a graph to scale with all the labels being really pretty is so that you can extract information from it. But looking at this graph, I can answer all of these questions below. Okay, so here we go. We're at the 10-minute mark almost, and we're just now getting to domain. Two different ways to do domain. First of all, I can look at the graph. Okay, now this graph is going forever to the left. This red arrow Okay? Even though it's going down, it's going forever to the left. So technically, this graph has no beginning, but it does have an end. It ends right there. It ends at 4. So 4 is the farthest point to the right that it goes. Okay? Now, without looking at the graph, just look at the domain. Look at all this domain stuff here. Okay? It goes from less than 0, which is all negative numbers, and where this thing ends, it picks up at 0 to 2, 2, 2, and then it ends at 4. So graphically it makes sense, and just by looking at the domain, if you put all these pieces, okay, all these pieces that I'm erasing, all this markings here, all these 4 if statements, if you put all of those in a blender, you're going to get from negative infinity to 4. All right, now the range. The range is the lowest value up to the highest value. Well, once again, looking at this red arrow here, this parabola, half a parabola, it's going down forever. So it technically has no beginning, but it does have a maximum point. Notice that it reaches to the height up here. It hits 3. Okay. All of these pieces here, they are not as high up as 3, so I don't need to look at those because I'm only looking at the highest possible values first. It goes up to the height of 3. Okay. And notice it's an open dot there, so I put a parenthesis there. And if you don't know how to write interval notation like this, see how I write these brackets and parentheses and negative infinity? There's another video called interval notation. You're going to have to go back and watch that. So I'm assuming you know how to write in interval notation. And then notice we have this floating dot up here at 4. Floating dot. So in my range, I state that the highest value is 3, but then I have this little weird dot floating up there. I have to include that also. And there's many different ways to write this, but I'm also just going to include 4. There's no interval. Between 3 and 4 is just kind of a dead zone there, okay? You have this floating dot up in the air, and so we just leave that. All right. So let's go to part C here, which is discontinuous. Okay, this is a calculus word here, but the word continuous simply means that the graph is continuous means smooth, or not having any gaps or holes. This graph is very discontinuous, meaning that it is not smooth. If you were riding a skateboard on the sky here you are, and you're traveling left to right, you're going to hit this hole here, and you're going to fall. So we would say it's discontinuous at 0. Notice I didn't write the number 3. This point is at the height of 3, but I'm only using x values here, okay? Only x values. And then we would hop down to this curve, and then there's also a hole at the number 2. It's discontinuous at 2. So the discontinuous points is where there is a gap or fracture or a hole in the graph. And those are the 2 parts where there is a hole. All right, let's talk about intercepts here. Just by looking at the graph, there's an intercept at, let's see, there's a dot here at 0, -3. Okay, just right there. Now, it's open-ended here. It says intercepts, so there could be more than one. That is the blatant y-intercept. I'm not going to use this point up here because there's a hole there. It technically does not touch the y-axis. It only touches the y-axis at 0, -3. And then notice that the blue piece touches the x-axis somewhere. Now, I don't know where that's at, that point there. And I'm making a mess of this graph, aren't I? Hope you're following me. But that blue thing touches the x-axis somewhere. Now, everywhere on the x-axis, the y value is 0. So I'm going to take the blue piece here. Blue piece right here. And I'm going to set that equal to 0. 2x minus 3 equals 0. Okay, and if you add 3 and divide by 2, you're going to get 3 halves, or 1.5. Okay, so the other intercept would be at 3 halves, comma, 0. So notice there are two different types of intercepts here. We have a y-intercept, that is where x is 0, and we have a x-intercept where x is 0. Okay, so intercepts can be on the x or the y-axis. Now let's finish up this graph here. Part F, which is intervals of increasing. This graph from left to right, the red branch is increasing and the blue branch is increasing. So the red branch is from negative infinity up to 0. Union from 0 to that blue branch goes up to 2. Okay. That little green dot up here is stationary. It's not going uphill or downhill, so we don't even consider that. It's not increasing or decreasing. And the only branch that is decreasing is my orange branch here. Okay. That orange branch is decreasing from 2 to 4. And notice once again, the only time I considered the y values is with the range. Everything else is using the y values, or excuse me, the x values on the intervals. Okay? Now, on the next frame, I'm going to graph the same exact function, but I'm not going to be doing the erase method. I'm just going to be plugging in values. It's going to be a little bit quicker, but if you are very comfortable with the erase method, stick with that, and good luck. Alright, so once again, I'm going to graph this function again, but I'm not going to be doing the erase method. I'm just going to be doing it directly. Now I still have a parabola here, and I'm going to start by plugging in 0. And if you plug 0 into the function, you're going to get a y value of 3. Now notice I'm writing an open circle there, because even though I plugged in 0, it technically, I'm cheating here a little bit, it can't equal 0. So even though I plug it in, I get the y value of 3. I put an open circle there to communicate not equal to. Now, I know that that looks like a parabola, and it's a sad face because the coefficient of x squared is negative, so it's going to be sad. But I'm only going to graph that to the left of 0. Okay? Now if I want to, I can plug in, isn't negative 1 less than 0? Yes, it is. Now if you plug in negative 1 into the function, negative 1 squared is 1, and 3 minus 1 is 2. So I can simply just put another point there to help me guide my graph. Okay? So notice I'm not doing the erase method, I'm just plugging in values to give me an idea what it looks like. That's the first piece. The second piece there, I'm going to plug in 0 into the function, plug 0 into there. If you plug 0 into that, you get negative 3. It's strictly greater than 0, so I'm going to put greater than or equal to 0, so I put a solid dot. Now I know this piece right here is linear, and Euclid said let's say 3,000 years ago, that between any 2 points is a straight line. So I'm just going to plug in 0, and then I'm also going to plug in 2. 2 times 2 is 4. 4 minus 3 is 1. So at 2, comma 1 is the end point. Between any 2 points is a straight line. Okay? Open. Okay. Now the next piece, the green piece is 4, and if x is equal to 2, there's nowhere to plug the 2 in, it's just 4. So 2, comma 4, dot, at the height of 4. Okay, let me erase this to give myself some room. The last piece, I recognize it is linear. So between any 2 points is a straight line. I'm going to take the 2, plug it in there. Negative 2 times 2 is negative 2 times 2 is negative 4. Negative 4 plus 2 is negative 2. So at 2, negative 2, it's going to be open because it's strictly less than. And then that is the beginning point. Now I'm going to plug in 4. 4 times negative 2 is a negative 8. Negative 8 plus 2 is a negative 6. So that means at 4, negative 6 is going to be the ending point. And so, yeah, this is, guys, not to scale here, but this point right here is 4, negative 6. Okay, so notice I was able to graph this without doing the erase method. One purpose why I do the erase method is that you just would recognize that all this is just overlaying a bunch of graphs that you're familiar with. And you're just considering the domains, the restricted domain here, and you're just considering that portion of the graph. Notice I just did this in 3 minutes by just plugging in the x values, and if it's linear, I connect it in a straight format like this. This is linear, so I know it's straight. This is linear, so I know it's straight. That's a quadratic, so I just connect it in a curvy fashion. Okay, thank you.